Welcome everyone to today's GOCC. Before I introduce the speaker, let me remind you all of our community statement, which is we are all learning, everyone has something to contribute, and no one has all the answers. The last point includes also the experts here in the round and the speaker, but don't be afraid to ask any questions. You can either unmute yourself or put them in the chat, and then the organizers will try to find a good time to interrupt our speaker to ask this question. With that said, it's my pleasure to introduce to you Bishal. He's one of the people regularly showing up in the seminar, so it's super nice for me that he's also giving a talk here, and he will be talking about combinatorics of continued fractions in the realm of permutations, and sorry, I cannot pronounce them.
Genoki numbers.
Genoki numbers. Thank you. Bishal, please take it away.
Yeah. So hello, everyone. I would like to begin by thanking Stefan and the other organizers for inviting me to give a talk at GOCC. And let me mention a few things about my talk before going into the details. I am not assuming any prerequisites for this talk. And so feel free to interrupt me at any point. I shall mostly be talking about a large part of this talk. I will be talking about well-established results. And towards the end, I shall touch upon some ongoing work with my supervisor, Alan, who is also here in the audience. Yeah, and so let me begin. By the way, I hope the font size and everything is all right. And so feel free to interrupt if you have any comments in general. Move this a little bit here. Okay. All right. So I have 3 parts in this talk. So I decided to go with a combination of slides plus writing because it's better for my audience, I guess, if to follow through while I'm writing stuff. So I have 3 parts, roughly. So there's part 1, which is where I will introduce continued fractions. There's part 2, where I will be focusing on permutations. And in part 3, I shall talk about Genoki and median Genoki numbers. All right, so let me begin. So we start by looking at a very simple identity. So we are working in the ring of formal power series, and in this ring, this, all of us know, this completely makes sense. So if we write 1 over 1 minus alpha 1 t, where alpha 1 is some element, then we have this identity alpha 1 squared, t squared, and so on. Now, what I'm going to do is I'm going to I'm going to do something to it. So, well, I'll have 1 over 1 minus alpha 1 t, but then I'll also do 1 over 1 minus alpha 2 t. And so when you expand, so when I write this, it's going to become 1 over 1 minus alpha 1 t times, I can expand this thing here. So I'm going to get this 1 over 1 plus alpha 2 t plus alpha 2 squared t squared, and so on. And then I can further expand this, and if I write it out, you're going to get something like 1 plus alpha 1 t plus alpha 1 squared plus alpha 1 alpha 2 t squared, and I'm not going to write the higher order terms. And so now all of us kind of, I guess, here would not be. So if I now say that if I take an expression of this form, 1 over 1 minus alpha 1t, 1 over 1 minus alpha 2t, 1 over 1 minus alpha 3t, and so on, and it goes on. If I say this, I guess by now you sort of believe that this thing would stabilize, and so you're going to get a continued fraction here on the left hand side. On the right hand side, you're going to get a power series. So you have coefficients t power n goes from 0 to infinity, and here you have some coefficients which are in infinitely many variables, alpha 1, alpha 2, alpha 3, and so on. And so alpha 1, alpha 2, alpha 3, and so on, they are in some nice ring, and you expand out this continued fraction, and you're going to get a formal power series, and each of these things are polynomials in the variables alpha, in the one parameter family alpha. So this, I'm going to use a different color. This continued fraction over here, it's called Stieltjes continued fraction, and these polynomials are called the Stieltjes-Rogers polynomials. And now you might be wondering, what does this have to do with combinatorics? Because we are in a talk about combinatorics, and where's the combinatorics? So we'll see that in a while. So yeah, so still just continued fraction, and these are still the Rogers polynomials. So before going, so consider a Dicke path, and I guess all of us here know what that is. Anybody? If okay, I mean, yeah, feel free to put it in the chat, and maybe one of the moderators can let me know. So we take a Dicke path, and we assign weights to each of the steps on the Dicke path. So if it is a rise, which I indicate by this northeast arrow, I'm going to assign a weight of 1. So this is going to get a weight of 1, 1, 1. All the black edges here are going to get weights 1, and so on. And all the falls are going to get a weight alpha I if it is a fall from I to I minus 1. So this is going to get, this is a fall from height 1 to 0. So this is going to get a weight of alpha 1. I'm going to assign this a weight of alpha 2, alpha 3, alpha 4, alpha 4 again, and then this is alpha 3. And if I declare that the weight of this Dicke path is the product of the weights of its steps. So I'm going to write that out, and that's alpha 1, alpha 2, alpha 3 squared, alpha 4 squared. And this is how I assign my weights. So now let me look at what happens if I fix the semi-length of the Dicke path and look at the first few cases. So if I take n equals 1, then this gets a weight. So I'm not going to write the weights for the rises from now on. This gets a weight of alpha 1. So the total weight of this is alpha 1. Here I get alpha 1 squared. Here I get alpha 1 times alpha 2. Oops. And if I add these up, I'm going to get alpha 1 squared plus alpha 1, alpha 2. Okay. Now, I'll do the example for n equals 3 again so that we get an idea of the kind of things. So this is going to be alpha 1 cubed because you have 3 steps, 3 falls from height 1 to height 0. This is going to be alpha 1 squared alpha 2. This is going to be alpha 1 squared alpha 2 again. Here you're going to get alpha 1 alpha 2 squared, and this is going to be alpha 1 alpha 2 alpha 3. And now when you're going to add all of these up, you obtain alpha 1 cubed plus alpha 1 squared alpha 2, but then this occurs twice, so twice of this, plus alpha 1 alpha 2 squared plus alpha 1 alpha 2 alpha 3. So and now I'm going to tell you why this is relevant. So the beautiful theorem which Flageolet proved in 1980 is that these polynomials, the Stieltjes-Rogers polynomials, are exactly equal to the weighted sum over all dict paths of a certain given semilength. And if you recall, this we had seen this alpha 1 squared plus alpha 1 alpha 2 that came up a few slides ago when we sort of saw the thing here. Okay.
I have a quick question.
Yes. Go on.
So dict paths, there's an easy involution where you just reverse them. Is there any particular reason? Do you know of any particular reason why you assign the weights to whenever you're falling as opposed to whenever you're rising?
You can actually do both.
Right.
So okay. Yeah. So I sort of did not say this. What you can do here is when you go from height, when you rise from height I minus 1 to height I, let's say we assign a weight of beta I, and then you get alpha 1, beta 2, beta 3 squared, beta 4 squared, because corresponding to every height is also a fall. So this would become a beta 1, this would be beta 2, beta 3, alpha 3, this would be a beta 3 again, and then beta 4 and so on. This would be a beta 4 again. So basically that would just be substituting each of the alpha i's to alpha I, beta I. And then your continued fraction would be alpha 1. This would be beta alpha 1, beta 1, alpha 2, beta 2, and so on. Yeah, so you can do that. Yeah, thank you.
I think I've seen a similar theorem where we had Motzkin paths and not dict paths.
So I'm getting to that.
Okay, perfect.
Great. So, so this is what I was going to say. So this is a picture of Flageolet. He died in 2011. This is from Wikipedia. And all right. So in fact, Flageolet proved a bunch of more general results, and this is only one of the results that he proved in his beautiful paper. In the same paper, as Stefan pointed out, he showed an equivalence. He gave a combinatorial interpretation for something called Jacobi continued fractions. So the previous one was still just continued fractions. This is called Jacobi continued fractions. And Motzkin paths. So dict paths are paths where you stay on the positive quadrant and you are only allowed either rises or falls. In Motzkin path, you're allowed rises, falls, and level steps. So these are steps from, say, k comma I. I'm not sure. Well, okay. Yeah, I guess it's understood what I mean by this. And so Jacobi continued fractions look something like this. So you have 1 over 1 minus gamma naught t minus beta 1 t squared 1 over 1 minus gamma 1 t minus beta 2 t squared 1 minus and so on. And the weights that you assign are, so these get weight 1, a level step from height I to I gets a weight of gamma I, and the fall from height I to I minus 1 gets a weight of beta I. Yes. And oh, by the way, and the proofs of these results are really simple, if you believe me. I'm not going to prove it right now in the interest of time, but they're not difficult, and you can write out a recurrence, and using that you can actually show this. So it's a beautiful result, and the proof is surprisingly simple. So now, having said this, here is a general problem that we have. So start with some combinatorial sequence, A0, A1, A2, A3, and so on, and consider its generating function, ordinary generating function. And then, so the goal is try and find continued fraction expansion of Still-Gist form, or maybe even Jacobi form if you are interested in that. And it is guaranteed that we have algorithms to show that these almost always exist. But we would be interested when the coefficients are nice. And one proof strategy is we first use computer experimentation to guess the coefficients alpha. And after we have guessed alpha, we then find bijectively show that this sequence is equal to, is counted by Sn of alpha. So, and okay. Now at this stage, I would maybe pause for about 10 seconds and see if there are any questions. So I'm going to start with part 2 of this talk now.
After you have stated the problem, did you say that in general it has a solution, or
you can, I think so you have algorithms where you can compute an S-fraction, but we would be interested in S-fractions with nice coefficients, whatever nice means in that context.
Okay.
Yeah, I think Stefan's question kind of melds with mine, where I was going, are we really guessing the coefficient? Well, I guess we're guessing the pattern, but I think like alpha can be computed recursively, because our first term corresponds with alpha 1, our first two terms correspond to alpha 1 and 2. So we're guessing a pattern for the alpha, but we're computing what the alpha would have to be, right?
Yeah. So we are exactly computing. So it's an infinite sequence, right? So generally the approach that we take is we put it on the computer, maybe compute the first 5, 6, 20, whatever computational power is available to us, get alpha 1, alpha 2, and so on, and then put it on the OEIS if they are nice integers.
Right, and then put it on the OEIS.
Yes. So I mean that's sort of our daily what we do. We look at, we're always looking at the OEIS in our work. So yeah. Any other questions or anything in the chat, or should I just move on? All right. So now let us look at some classical examples of Still-Gist continued fractions. And Still-Gist, the values of alpha for, okay, I think I have, there's some difference in notation there. Okay, maybe this should be alpha 1, since I begin with alpha 1, alpha 2, and so on. Yeah, sorry about that. So Catalan numbers are, of course, counted when you put all the alphas equal to 1, because then you are just counting Dickwats. Permutations are given by, so for permutations, the sequence is 1, 1, 2, 2, 3, 3, 4, 4, and so on.
Is there a nice projection directly?
These are given by 1, 1, 1, 2, 1, 3, 1, 4, and so on. Number of, so semi-factorials, so these numbers look like 1 times 2 times, 1 times 3 times 5 times so on till 2n minus 1. So let me maybe write out. This is equal to 1, 3, 5, 7, so on till twice n minus 1. The alphas here are given by 1, 2, 3, 4, 5, and so on. So these are some of the known alpha sequences. And in fact, some of these were already known to Euler over 250 years ago. And this includes the sequence for the continued fraction for permutations, for factorials. So you have, this is the generating, ordinary generating function for permutations. And here you have the still just continued fraction, 1, 1, 2, 2, 3, 3, and so on. And Euler proved it analytically, whereas there are also several bijective proofs of this result known. So some of these are, there's a bijection by Francois and Viennot from 1979 that can be used to prove this. So Francois and Viennot, they were investigating orthogonal polynomials, and so this came up in the combinatorial theory of orthogonal polynomials. Fuata and Zellweger and Bian, their work was towards, so they were looking at permutation statistics and equidistribution of pairs of permutation statistics and stuff like that. That is where that came up. And so using and these are using these bijections, you can prove this identity combinatorially. So on one side you have permutations, on the other side you have big paths with certain weights on the edges, on the steps. In fact, Euler had something even more general. So instead of having 1 factorial, 2 factorial, 3 factorial, and so on, Euler had a still just continued fraction for when you have x, so rising factorials in terms of x. So this is x times x plus 1, x times x plus 1 times x plus 2, and so on. And the sequence of alphas are x1, x plus 1, 2, x plus 2, 3, and so on. So of course, when you plug in x equals 1, you get factorials here. So this is a line of investigation that we sort of are interested in, and so let me now maybe rewrite this. So if you take 1, 1, 2, 2, if this is your alpha sequence, 3, 3, and so on, this gives, so if you expand it, it gives ordinary generating function for permutations. If you instead replace, if you do x1, x plus 1, 2, x plus 2, 3, and so on, it gives, we can think of it as giving ordinary generating function for permutations along with a statistic where x counts the number of cycles. So these are, so the coefficients are Stirling numbers of the first kind, or Stirling cycle numbers. So the coefficients that you obtain here, if you expand this out, this will give you the number of permutations. So coefficient of x power I here is the number of permutations on n letters with I cycles. Now instead, you can, one could do this, right? One could have x and then y and then x plus u, y plus v, x plus twice of u, y plus twice of v. And so certainly what you would get is an ordinary generating function for permutations along with some statistics, y, u, and v. And then you can ask what these statistics are. And this is the kind of stuff, this is the kind of investigation that we are interested in. And this particular question was answered by Sokal along with Jiang Zheng in a recent paper that came out on the arXiv, I think, 2020 and published soon. So, so they have, okay, so we call the polynomials that we obtain as Pn of x, y, u, v. So when you put in Pn of x, 1, 1, 1, that's just equal to x times x plus 1 times x plus n minus 1. So these are the polynomials that you obtain. So these are the coefficients that you get from when you expand the ordinary generating function. So they showed that these polynomials Pn, x, y, u, v, they have two different combinatorial interpretations. So I'm not going to go into the details of these, but they could interpret these. And so the first one, I'll use a different color. So the first one is a variant. So this uses the Fouata-Zeilberger bijection to explain it. Sorry. The second one uses Bian's bijection. And you can also do a version that uses Franson-Vienno. So the thing is, in fact, this result, I mean, both of these results is in fact a special case of a much more stronger theorem, more stronger results that they have. And they do not have interpretations just for 4 variables, but they have 5 families of infinitely many variables where you interpret 5 families of infinitely many statistics. And similar results were also found by Blitwick and Steingrimsson at around the same time in a similar context, not exactly similar. And there was a lot of activity along these lines in the past 20 years. Several people have worked on it and were building up. However, it turned out that there was already a paper by somebody called Randriano Rivoni that he had published in 1998, and this paper was just not known, and almost all the results were known in full he knew almost all these results in full generality in this paper. So it's surprising, I mean, how this was just undiscovered for 20 years, and people were working on building it up. So okay, now. So this is the investigation. So we have a combinatorial. Now let's flip it back. Let's, instead of starting with the ordinary generating function for permutations, we start with the continued fraction. So we have a combinatorial interpretation for the sequence 1, 1, 2, 2, 3, 3, and so on. And we can also read statistics by introducing variables, so that when you specialize those variables, you obtain exactly these coefficients. How about, so now we can ask a more general question, which is, what if I give you the sequence of alphas to be 1 power k, 1 power k, 2 power k, 2 power k, 3 power k, 3 power k, and so on. What happens? Can we interpret this? And so let's look at the first few. So of course, when k equals 0, you get Catalan numbers. When k equals 1, you get n factorial. When k equals 2, you get something called the median Genoki numbers. And when k equals 3, the sequence is not on the OAS. In fact, you can ask for, in fact, what you can try and ask is, can we have, well, okay, so if you remember the few examples that we had, all the coefficients were sort of linear they were increasing linearly. Whereas when you increase k, they will increase, so this is increasing constantly, increasing linearly, quadratically, cubically, and so on. So it sort of gives some sort of a complexity class for classifying combinatorial objects which have nice continued fractions. And so the idea is to try and find some canonical objects where explain for each class. So for linear, there are several. So some of these we had seen so you have set partitions. This increases linearly, permutation increases linearly. Well, not exactly linearly, there's like, but quasi-linear would be more appropriate term. This double factorials increase linearly. So now you have a lot of other sequences where it could go 2, 4, 6, 8, 10, and so on and so forth, or maybe some sequences increase quadratically. But so these sequences 1 power k, 1 power k, 2 power k, 2 power k, and so on seem to be the most natural choice for that degree. And so this is more or less sort of driving our research. A part of our research is can we understand this complexity class? And okay, to start with, we would like to maybe obtain a natural candidate to explain each of these classes for each degree. And at this point, I am at the end of part 3, and I would like to pause here if there are any questions. Maybe I'll pause for 10 seconds and then I'll move on.
Well, I have a question. I wonder what happens if you say, set all of the alphas after, say, after position k to be 0, and is the resulting power series agree with the full power, or with the original power series up to a certain number of terms depending on k?
The answer is yes. Yes.
Okay.
So that's because you in fact you can see this when you think of it in terms of the combinatorial interpretation. So when you are setting alphas after a certain thing to be all equal to 0, that just means that you're restricting the height up to which your dig path can go. So you're only allowing dig paths of a certain height.
Yeah, and then do you get anything interesting, say, if you set all the alphas to 0 except for one of them?
Oh, okay. So if you set, I mean, okay. So if you have any alpha not equal to 0, that has to be alpha 1. Otherwise, it's going to vanish.
Oh, sure, of course, yeah.
Yeah, and if you have a finite number of alphas, which exist and everything else is 0, what you obtain eventually is a rational function.
Okay. Yeah.
Yeah. So whereas with this, I mean, so the generating, so it would generate some object which is rational. Whereas this can generate, I mean, yeah. So this can, for example, permutations do not have a rational generating function. So, or even Catalan numbers have an algebraic generating function. But then, yeah. So I think, yeah. So I guess I think this is always true. I'm not sure if you have an object given whose ordinary generating function is a rational function. Then you get finitely many alphas which are non-zero. And any other questions? Okay, so all right, maybe I'll proceed, and I see that okay. So now this is part 3, and I'm going to talk about Genoki numbers. And Genoki numbers are given by, so they are given by, well, they were first described using, one of the first descriptions of Genoki numbers was using this power series expansion. So you take, so they are related to the tangent numbers and Bernoulli numbers and a lot of other different numbers. So if you expand t tan t over 2, you get this expansion, and these are the first few numbers look like 1, 1, 3, 17, 1, 5, 5, 2, 7, 3, and so on. So before going to median Genoki, I would first like to tell you what Genoki numbers are. And then there's an alternate way of, okay, there's an alternate way if we want to compute these numbers. So there's something called a Booster-Pedron algorithm, quite a mouthful for me. So they can be generated like this. So we start with 1, and I write 1 again. And then what I'm going to do is I'm going to go from left to right first. I'm going to look everything that's on top and add them up. So there's just a 1 here. So I write it 1, and then I do a 1 again. Now I go from left to right, and there's just a 1 on top. So I'm going to write a 1. And at this position, there's 2 1s. So I'm going to add these 2, and I'm going to get a 2. Again, so first I go in this direction, then in this direction. Again, I'm going to go this. So I have a 2, and then 2 plus 1, I get 3. I'm going to copy the 3 again. I'm going to go back again in the reverse direction. I get 3, and then 3 plus 3 gives me 6. 3 plus 3 plus 2 gives me 8. I'm going to go in this direction now. I have an 8. 8 plus 6 gives me 14. 8 plus 6 plus 3 gives me 17, and so on. So I'm going to copy the 17 again, and I'm not going to write more. And now you can see that 1, 1, 3, 17 appear here. So you have 1 repeating twice, 1 repeating twice, 3 repeating twice, 17, and then next row you'll also have a 17 over here, and so on. So the Genoki numbers are what you obtain as the rightmost entries here on this table. On the leftmost, you get the sequence 1, 1, 2, 8, and so on. And these are what are known as the median Genoki numbers. So this is how the Booster-Pedron algorithm would look like. This is exactly what I did. So these are the Genoki numbers, and then these are median Genoki. And so and then now there are several combinatorial interpretations for these numbers. So let me mention. So Genoki numbers are given by a subset of permutations. So you take permutations sigma in S2n such that you have, whenever you have an even, something even, so twice I is bigger than sigma of twice I, and twice I minus 1 is less or equal to sigma of twice I minus 1. where I lies in 1, 2, 3, so to n. So this is an interpretation for Genoki numbers. This is a class of permutations with length 2n. Median Genoki numbers. You can count them by this almost the same thing. Oops. Sorry about that. Almost the same thing, but you have an equal, so you could do two things. This counts median Genoki, Hn, and if you put equalities in both, this also counts median Genoki, but one's shifted. And this counts Genoki. So both median Genoki, and so when you have inequalities on one of the two, you get Genoki, and when you have inequalities on either strict or weak, whatever, on both of these, you get the other. And these were sort of first introduced by Lazar and Vaux, and they call it depermutations. These were introduced by I think Dumont, and were known as Dumont permutations, but we call these DE semi-derangements because it's almost a derangement, but not exactly. Sorry. E for even, because it's, and when we have inequalities, strict inequalities in both, we call these D-derangements. So let's look at an example of depermutations. So you have twice I bigger than or equal to sigma twice I minus 1 is less or equal to sigma twice I minus 1. So what that means, so I have, so I'm going to write my permutation as a bipartite graph. So I'm going to say where 1 goes to. So let's say 1 goes to 7. So 1 is only allowed to go to something bigger than it. Because for odd numbers, you go to something bigger. 2 can go to either 2 or 1. So let me send 2 to 1. 2 cannot go to anything bigger. 3 goes to 3. I'm allowed fixed points. Let me say 4 goes to 4. I'm going to send 5 to 6. So whenever I'm odd, I go to the right. I send 6 to 2. I send 7 to 8. And finally, there's only one thing remaining. I send 8 to 5. So sigma is equal to 7, 1, 3, 4, 6, 2, 8, 5. So this is a depermutation. And this is an example, a non-example of a depermutation because 2 goes to something bigger and 3 goes to something smaller. So the sequence of median Genoki numbers, so if you take these numbers, this has alphas as 1, 1, 4, 4, 9, 9, and so on. And so I shall now maybe quickly show you a sketch of a bijection, how to show this. So let me tell you the setup of the bijection. So on one side, we have depermutations. Actually, sorry. So this is the sequence Hn. So these are D-derangements. So I do not allow fixed points. So this example that we saw won't work because you have fixed points 3 and 4. So these are basically depermutations which do not have any fixed points. So on my left-hand side, I'm going to have the derangements. On my right-hand side, I have dig paths, and a step. So if I have a rise which goes from I minus 1 to I, I can label it from the set 0, 1, so on till I minus 1. And if I have a fall, then going from I to I minus 1, I give it labels from 0, 1, so on till I minus 1. And the cardinality of the number of dig paths is the Stieltjes-Rogers polynomial Sn of alpha, where the alphas are given by 1, 1, 4, 4, 9, 9, and so on. Because for every up step, you have I choices from height I minus 1 to height I. For every down step, you have I choices. And so you have, when you write out the S fraction, you have I squared choices for each. So this is my set of paths. And this bijection is given in 2 steps. So step 1, I'll just write out. Maybe if I have time, I don't think I have time. So step 1 is giving us surjection from the derangements to the derangements on 2n letters to dig paths with length 2n. Step 2 is, once I know what the dig path is, assigning the labels. So step 2 is more complicated. I'm not going to go to that, but I can quickly tell you what step 1 is. So for step 1, what you do is, if sigma so you look at your depermutation, you ask if sigma inverse of I is even. And remember, this is the same as saying that sigma inverse of I is strictly bigger than I. Then you say that it's a rise. If sigma inverse of I is odd, then that's the same as sigma inverse of I being less than I. Then I say it's a fall. And this is how I obtain my dig path. And maybe with that, I will quickly conclude, because I do not have time remaining. So I'll just jump over to our final result that we've obtained so far. So we in fact have a continued fraction not just for D derangements, but for all D permutations. But then in that case, we sort of require not an S fraction, but something called the T fraction. So Thron type continued fraction, so T fraction, where we have this, it's much weaker than a general T fraction. We have an extra delta 1 T term here. These are given by Schroeder paths of a special kind. So I allow rises, falls, and I allow a level step where this goes from height from only at height 0. So from k0 to k plus 2, 0. So and the kind of paths that we get are Schroeder paths, and we have depermutations, but we can do depermutations with statistics, and so we have a 10 parameter family of 10 parameter statistics, and we'll eventually obtain maybe a 5 or 10 parameter family of infinitely many variables, sort of similar to what Sokal and Zeng did in their paper. And there's also been some recent result by Pan and Zeng, and they have used a different combinatorial interpretation of median Genoki and Genoki numbers, and they obtain other statistics. And with that, I would like to conclude. Thank you.
Thank you. Let's all thank our speaker. And I open the stage for questions.
I have a question.
Yeah.
Hi, Vishal. Thank you for a lovely talk. That was really, really lovely. I really enjoyed that. Could you go back to the slide with the, was it a Browstepedron?
Boostrophedron. Yeah, it's quite a mouthful, isn't it?
Boostrophedron. I have a probably quite predictable question for you. This is a triangle of integers, which is wedge-shaped. Can you say anything about the total positivity of this array?
No, maybe I can't. Maybe Alan can.
Is it TP?
I don't know. Alan, do you know if you're around?
No, I don't know. Well, okay, if you look at the whole array, it's clearly not, because you see right there this 2, 3, 8, 6.
Oh yes, missed that. Yes,
but but that's probably not the right thing to look at. Probably you should look at the subset of even rows or the subset of odd rows.
Mm-hmm.
And I don't remember. I think I asked myself the question too, but I don't remember the answer.
Okay, good to know.
I mean, the truth is, I don't understand this Boostrophedron algorithm very well. I mean, it's quite amazing, right? It's a recurrence with no choice of initial condition. I mean, there's no freedom of initial condition. You start with 1, 1, and you get what you get. And it turns out to be Genocky and median Genocky. I really don't understand what's going on here. Maybe someone who understands can explain it to us. But it's one of the ways of defining Genocky and median Genocky.
Yeah. Thanks for the question, Tomak.
I actually had kind of, while we're at the slide, so the what was the term for that? The D permutations were defined on the symmetric, only on the even symmetric groups. But it seems to me like the definition works perfectly well on the odd symmetric groups. It's just your last number is always forced to go to itself, and so you haven't done anything interesting. Which reminds me of the slide where we just skipped every other number because they weren't interesting, but they are the exact same as the previous one. And so I was wondering if this triangle had a deeper connection with these D permutations, like maybe some of the coefficients on the interior started.
Possibly. So, okay, so let me tell you that. Yeah, I mean, that could be, I'm not sure. I haven't thought about it. Yeah, thanks for the comment. I mean, so yeah, as you've pointed out, if you take, it doesn't make much difference because then for odd indices, I mean, for the last thing, it will be fixed. So it will be counting the same thing. And so essentially, if D permutations, you'll for even and odd, you'll get this sequence 1, 1, 1, 2, 2, 8, 8, 56, 56, and so on. And now, if you look at these rows, so if you then do a semi-derangement, you obtain you get the Genocky numbers. So maybe the stuff in the middle probably counts some class of permutations that interpolate between the permutations and the E semi-derangements, where you that might be the case, I guess.
Okay, yeah, just
thanks for the comment.
That we were throwing out all the odd ones twice, and I was like, oh, well, that's interesting.
Yeah, that's a really interesting idea to try to interpret all the coefficients in this Boostrophedron array. Thank you for that.
So I have one question. So you have shown us a little bit about this median Genocky numbers. On the right side, how is there this rejection to dig paths, or is the?
Oh yes, they do. So the coefficients, I have the list of coefficients somewhere with me. So maybe I can write out. So the alphas for Genoki, it is so it's 1 times 1, 1 times 2, and then 2 times 2, 2 times 3, 3 times 3, 3 times 4, I think 4 times 3 after that. Can't erase it. Zoom. Anyways, yeah, so it goes something like this. For median Genoki, as I said, so it's 1 times 1, 1 times 1, 2 times 2, 2 times 2, 3 times 3, and so on. For one's shifted median Genoki, the sequence looks like 1 times 2, 1 times 2, 1 times 2, 2 times 3, 2 times 3, 3 times 4, 3 times 4, and so on. So yeah, they do have nice coefficients as well. And in fact, I mean, all of these are quadratic, as I had mentioned. And so our most general thing that we have with several variables, you can actually obtain D derangements and DE semi-derangements and so on by specializing some of these variables to be 0. And so you then get those as special cases of this more general thing. Turning off some statistics. Yeah.
Okay, we are hitting the full hour. So I guess it's time to thank the speaker again. And then maybe we can ask some informal questions afterwards again. So thank you.
Thank you for coming.